Hello, everyone. Today we're going to talk about Section 2.2, Introduction to Counting Methods. In the last section, we saw that there are 3 steps to finding the probability of an event. Count the number of outcomes that satisfy the event, count the total number of possible outcomes for the experiment, and then divide these two values. When the experiment is simple enough, we were able to count the outcomes by simply listing them out. However, if we want to look at more complicated experiments, we will need to find more sophisticated techniques. Perhaps the easiest tool for counting is to visualize the steps of an experiment using a decision tree. At each step, the tree splits into branches for each of the possibilities of that step. So example 1, flip a coin. If it's heads, flip it again. If it's tails, roll a 4-sided die. How many different possible outcomes are there for this experiment? So we go to our 4-step problem-solving process. Step 1, understand the problem. This experiment comes in 2 steps. First, flip a coin. Then, depending on the result of the first step, you might flip a coin again, or you might roll a die. Step 2, devise a plan. Our plan is going to be that we can visualize this experiment by sketching a decision tree. So step 3 is carry out the plan. The first step is to flip a coin, which has 2 possible outcomes. So from our start, one possible outcome that we have a branch of the tree is heads. The other possible outcome, the second branch of the tree, is tails. From there, the heads branches out into heads or tails because we would flip another coin if we flipped heads. The tails, if that came up, we would be rolling a 4-sided die, and the 4 possibilities there would be a 1, a 2, a 3, and a 4. So looking back at the result, we would count the number of branches in our diagrams. There are 1, 2, 3, 4, 5, 6 possible outcomes to this experiment. Heads, 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 tails, tails 1, tails 2, tails 3, and tails 4. Notice in the last example that the outcomes of the experiment are not equally likely. Let's go back and look. Because there's fewer outcomes for flipping the coin than there is for rolling the die, it is more likely to go heads, heads than tails 1. Consider next the experiment of flipping 3 coins. The steps of this experiment are independent of each other. The result of one flip does not affect the other flips. Because each step is independent, the outcomes of this experiment will be equally likely. So example 2, flip 3 distinct coins. How many different possible outcomes are there for this experiment? Step 1, understand the problem. This experiment has 3 steps. First, flip a coin, then flip a second coin, finally flip a third coin. Step 2, devise a plan. We can visualize this experiment by sketching a decision tree. So let's carry out the plan. The first step is to flip the first coin, which has 2 possible outcomes, either heads or tails. Next, we split each of these branches into the 2 possibilities for the second coin flip. So if the coin came up heads and we flip it again, our results are either heads, heads, or heads, tails. If the coin came up tails first and we flip it again, the 2 options that come from that are tails, heads, tails, tails. Finally, we split each of these branches into the 2 possibilities for the third coin flip. So we end up with heads and tails for the third, heads and tails for the third, heads and tails for the third, heads and tails for the third. And we have that for each of 4. So overall, we can count 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes for the experiment. Heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So as we make our branching tree, listing the possibilities for the first flip, and then after the second flip, and then after the third flip, when we're done with the third flip, the experiment's over and we can just count how many possibilities we had in that third and final layer of the tree. Tree diagrams can help keep us organized, but for large sample spaces, they are really no more effective than simply listing the outcomes. So our search for counting methods continues. Consider now the experiment of rolling 2 6-sided dice. To visualize this, we will depict the first die as black with white pips and the second die as white with black pips. Then we can just list out the sample space for the experiment as the sample space S is the set containing all our possibilities. The first row, we have a roll of 1 on the black die, along with all the possibilities of the white die, 1 through 6. The second row would be rolling a 2 on the black die, along with all of the possibilities for the white die, again, 1 through 6. We repeat this again. The third row has 3 on the black die. And then the white die is all of the possibilities 1 through 6. Fourth row is a 4 on the black die. Fifth row is a 5 on the black die. Sixth row is a 6 on the black die. And again, each of those rows has the white die having all the possibilities of 1 through 6. With all of the possibilities listed in the sample space above, we can count that there are 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So 6 times 6, 36 possible outcomes here. Notice I didn't just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on to get up to 36. I multiplied 6 times 6 because the 36 outcomes are organized into 6 rows and 6 columns. The outcomes themselves fill the area of this rectangle that's 6 rows by 6 columns. So 6 times 6 is 36. We generalize this result as the counting principle. The counting principle is a powerful tool for finding the number of possible outcomes without needing to list every possibility. Let's look at the definition first and then come back. Given an experiment which combines 2 independent simple experiments, the number of possible outcomes for the new experiment is the product of the number of possible outcomes for the 2 simple experiments. So we rolled the black die. There were 6 possible choices. We rolled the white die. There were 6 possible choices. The 6 for the black die times the 6 for the white die give us the 36 total possible outcomes. So the counting principle says when we have 2 experiments like this and they're independent of each other, we can just multiply the 2 possible outcomes together. Example 3, consider the following lottery game. 3 pots contain numbered ping pong balls. The first 2 each contain the numbers 1 through 9. The third contains numbers 10 through 25. To choose the winning lottery number, 1 ball is drawn from each of these pots. How many different winning lottery numbers are possible? So let's understand the problem first. We can think of this situation as an experiment in 3 parts. First, we draw a number from 1 to 9, so there would be 9 choices there. Second, from the second pot, we draw a number from 1 to 9, so there's 9 choices there. And third, from the third pot, we draw a number from 10 to 25. 10 to 25 would be 16 choices if we count them out. We're asked to find the total number of possible outcomes for this experiment. So step 2, let's devise a plan. The 3 parts of this experiment are independent. Drawing from one pot will not change what happens in another pot. Thus, we can use the counting principle to calculate the total number of possible outcomes. Let's carry out the plan. The counting principle simply tells us to multiply together the number of possible outcomes for each part of the experiment. So there were 9 in the first part, 9 in the second part, and 16 in the third part. We multiply together 9 times 9 times 16, and we get 1,296. So looking back at our result, there are 1,296 possible winning lottery numbers for this lottery game. Now let's talk about something called the factorial. Consider an experiment of drawing cards from the top of a deck of standard playing cards. Each time you draw a card, there is one fewer card in the deck for the next draw. Working with an entire deck of 52 cards is a little too much at once, so let's start with a smaller pile of cards. For example, consider taking only the ace through 5 of diamonds from a standard deck. So our sample space would be the ace of diamonds, the 2 of diamonds, the 3 of diamonds, the 4 of diamonds, and the 5 of diamonds. How many different ways are there to rearrange this stack of cards? Well, first we have a choice of any of the 5 cards to be the first card in the stack, so 5 choices. For the second card in the stack, one of our choices has been taken, but we could use any of the 4 remaining cards, so 4 choices for the second. We now have used 2 cards. That leaves 3 cards remaining to be the third card in the stack, so 3 choices. Using a third card leaves us with 2 possible cards remaining for the fourth card in the stack, 2 choices. Finally, for the 5th card in the stack, we only have 1 card left, so 1 choice. Using the counting principle, we find that we have 5 times 4 times 3 times 2 times 1, which is 120 possible ways to rearrange this stack. Following the pattern we see in this example, we would expect that if we worked with a larger stack, say 7 cards this time, we could calculate the number of ways to rearrange the cards as 7 times 6 times 5 times 4 times 3 times 2 times 1, which would be 5,040. This pattern of multiplying together a decreasing sequence of numbers is so common that mathematicians invented a notation to write it more easily. So let's define the factorial. We denote and define the factorial of a natural number n as n exclamation point, n factorial, which would be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So let's look at example 4. The school's athletics director likes to shuffle around the trophies on his display shelf. If he has 8 trophies on display and changes the order of the trophies every day, how many days will it take before he has used every possible order? So step 1, understand the problem. We are interested in the number of different possible rearrangements of 8 trophies. Step 2, devise a plan. Since we are rearranging all of the elements of a set, we should use the factorial. For instance, when we carry out the plan, we use a calculator and find that 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. The times 1 really isn't necessary because that doesn't change the value. We would get 40,320. So the athletics director could rearrange the trophies every day for 40,320 days, slightly more than 110 years, before he's used up every possible order. Example 5. The barbershop quartet Fred sings a gag where they attempt to pronounce words formed by rearranging the letters in their names. For example, DFRE might be pronounced da-free. How many different such words could these performers use? When we go to understand the problem, we find that we're interested in the number of different possible rearrangements of 4 letters. Devise a plan. Since we are rearranging all of the elements of a set, we should use the factorial. Step 3, carry out the plan. Using a calculator, we find that 4 factorial is 4 times 3 times 2 times 1, which is 24. Looking back at our result, Fred have 24 different words to choose from, including the correct spelling of their name. So if you have a calculator that has that exclamation point or the factorial function, you can use that. Otherwise, to find something like 4 factorial, you multiply 4 times every number underneath, 4 times 3 times 2 times 1. And that's section 2.2. Go ahead and do the homework for section 2.2. And when I see you next, we're going to go over the homework from both section 2.1 and section 2.2.